Thank you very much for that fantastic intro, Stuart. As he said, my name is P. Lawrence, and over the next half an hour or so, I'm going to introduce you to one of my favourite astronomical objects, the Moon. Now, over the course of half an hour, I can't go into a tremendous amount of detail on imaging and observing it, so I'm hoping this is going to be an introduction to you, and hopefully that will stimulate you to go outside and have a look at this absolutely wonderful object. We've got my... Have I got to do so? Oh, all else fails, plug it in. It is blank. That's supposed to be blank. Yeah, that's good. Okay. So we go through the next. I can probably this one. Okay. Wonderful. Thank you very much. Yes, so over the next half an hour or so, I'm going to introduce you to this most wonderful object. Now, just to recap on the Moon is the nearest natural neighbour to the Earth. It sits at a distance of about 400,000 kilometres, or in miles, that's about 250,000 miles. It has a diameter of 3,475 kilometres, or 2,163 miles. And an object that size, that far away, is actually large enough and close enough to actually subtend a decent size in the sky. So if you go out on a night when the Moon is up, you can see the Moon as a disk, and it has tangible features on it. Now, the Moon is gravitationally locked to the Earth, so as it goes around us, we always see exactly the same face pointing back towards us. So that's a very familiar face whenever you look up at the Moon. It's always the same features that you see. But when I say it's always pointing directly towards us, that's not quite right, because it actually does wobble and rock a bit on its position. And the reason for that is that the Moon's orbit is tilted to the orbit of the Earth by about 5 degrees, and that allows us to see a bit above it and a bit below it, depending where it is in that position. And it's also, the orbit of the Moon around the Earth is elliptical, so the Moon's speed as it goes around the Earth varies, and that allows us to see around the sides of the Moon. And taken together, those effects are known as libration. And you can see this is taken over 2 consecutive nights, and it shows the rocking motion of the Moon there. You can see a little bit around the edge of it as it goes. So in total, there's only 41% of the Moon we can't actually see. Now, the time it takes for the Moon to go around a full set of phases, and I'll mention the phases in a second, is 29.5 days. So if you have a particular phase of the Moon up in the sky, 29.5 days later, you'll have the same phase up in the sky, and that's called the Moon's synodic period. Now, the phases of the Moon are due to the fact that the Moon is essentially a sphere. It's not quite a sphere, but we can regard it as a sphere. So with the light from the Sun coming from one direction, half of that sphere is illuminated. And we get to see different aspects of that illuminated hemisphere depending on the angle between the Sun, the Earth, and the Moon. When the Moon lines up with the Sun in the sky, and because the Moon's orbit is tilted by 5 degrees to the plane of the Earth's orbit, what tends to happen when that occurs is the Moon either passes above the Sun or below the Sun in the sky. Occasionally it will line up perfectly and it will cover some of the Sun's disk, and that gives us what we know as a solar eclipse. But for the most part, the time when it actually lines up with the Sun, it's above or below the Sun's sky, and that's the point where the lunar calendar sort of resets to day 0, and that's the point known as new moon. As time goes on, the Moon moves around its orbit, so we start to see another bit of that hemisphere, a little bit of that hemisphere creeping into view, and that's when we get the early crescent phases. As the crescent phases are growing, they're described as being waxing crescent phases, so this part of the orbit here. When the Moon goes 1/4 of the way around its orbit, we see half of the Moon illuminated in the sky, and that gives us what's known as the first quarter moon. As time goes on, so we get even more illumination, we go into the gibbous phases, and again, because they're growing, they're called the waxing gibbous phases. until eventually the moon appears in the opposite part of the sky to the sun, and that's when we get full moon. Again, because of the tilt, the moon tends to go above or below the Earth's shadow in space, but occasionally they do line up, and then we get a lunar eclipse. Okay, so we've got full moon here, and then after full moon we get a reverse of the phases we've just had. So we go back through the gibbous phases again, getting ever thinner, and they're called waning because they're on the decline. When the moon has gone 3/4 of the way around its orbit, we get to the last quarter moon. So the last quarter refers to the fact it's on the last quarter of its orbit. And then it goes back towards new moon, we're getting back into the crescent phases again, so the waning crescent phases. I should also point out that the last quarter moon gives us a half of the moon illuminated, and it's the opposite half of what we had at first quarter. Okay, so let me jump tack a little bit here, change tack a little bit here, and go straight into lunar photography. Now, I live on the south coast, and occasionally the moon happens to be in the right position that as we're walking along the promenade at the front, you can get the moon rising above the sea horizon, and it can look quite spectacular. It looks huge when it's close to the horizon, which is purely an illusion, a moon illusion it's called. It's actually no bigger than it would be if it were up high in the sky. In fact, it's actually slightly smaller. But it does look wrong or right, larger than it should be. So of course people are there with their cameras, smartphones, etc., and they want to take a picture of this, and they're holding them up, taking a picture of the moon. Now Mr. Smug here, walking along on the promenade, knows that those pictures probably aren't going to come out very well. And the reason for that is that the moon is quite tiny in the sky. In fact, it's that tiny. If you hold your little finger up at arm's length, you can easily cover the disk of the moon without any problem at all. It is a tiny, tiny disk. So to get any decent scale on the moon, you have to use a reasonable amount of focal length. That's, I think, using a 500mm lens, if I remember correctly. And if anybody has ever been to St Patrick's House down in Selsey, they'll immediately recognise that very iconic weather vane. Patrick lives in Selsey, I live in Selsey, and Selsey is well known for its giant seagulls. Now, to get that focal length, you can either spend an awful lot of money on very long focal length lenses, which become extremely heavy to carry and difficult to work with, or if you have a telescope, you can combine the telescope. If you've got a DSLR camera where the lens comes off the front, you can combine the camera and the telescope together. And to do that, you need to use an adapter ring which is suitable for your particular make of camera. And there are guys out there, I'm sure, who are selling kits like that, so go and ask them if you're interested. That ring will have inside it a female T-thread, and then you get a barrel which fits into the eyepiece holder of your telescope, which has got a male T-thread on it. So they screw together, that goes in the front of your camera, and then that slots straight into the back of the telescope. So the telescope just becomes a super telephoto lens. And when you do that, you start getting a much larger disk of the moon on the face of the frame. That's actually taken with my beloved Vixen 4-inch refractor, which has got a focal length of 918mm. And you can see that's a reasonable scale across the disk of the frame. That's the full frame there. But even then, you're not really picking up a tremendous amount of detail in terms of the features on the moon's surface. If you want to do that, you've got to spend an absolute fortune, of course. You don't have to at all. This was actually taken with a telescope which was set up looking at the moon and a smartphone pointed down the eyepiece in a process called digiscoping. And that's a very easy thing to do. If you have a telescope at home, set it up on the moon. If you've got drives on the telescope, it makes it a lot easier. Just turn them on and then point the phone down the eyepiece, or if you've got a point-and-shoot camera, point it down the eyepiece, and if you can hold it square enough, let the automatic functions in the camera take over, and then press the shutter button, you get a picture like that. If you have a point-and-shoot camera, have trouble holding it in place, then there are these strange-looking devices you can get, which are called afocal coupling platforms. Again, I'm sure the guys out there can help you if you need one of those. You basically you screw your camera onto that, and that clamps around the eyepiece holder, holds everything in position. Okay, so let's now go back to look at some of the things you can photograph with the moon. One of my passions is going out and trying to get either the very young or the very late crescents of the moon. The young crescents of the moon are when, just after new moon, you can see it in the early evening sky, normally best seen around the spring months, or the late crescents are before new moon is about to occur, seen in the early morning sky, best seen in the autumnal months. And there is a photograph, I think that's about a 19-hour-old crescent moon. And you're thinking, what is he talking about? There's nothing on there. But it's actually, I don't know if you can see it there. That's impressive, isn't it? There's an easier one to see. That's a later crescent moon. You can just see the crescent hanging there in the sky. That's about 26 hours before new moon. And my earliest ever is this one here, which is 15 hours 13 minutes after new moon. In fact, that's where it is in the photograph. You can hardly see it at all. If you actually stretch the photo once you've got it, then it becomes visible. Now, there are people that go out there and they're passionate about this, and they do strange things like having masks up and infrared filters to try and capture these very early young crescents. But the ultimate new moon, I suppose, has got to be that one, where you take a photograph of the moon when it exactly lines up with the sun. So that's a great excuse to go eclipse chasing. Now, if you're looking at that and you're thinking, I can see detail on the moon there, well, think about it. If you were actually on the moon at the time of a total eclipse of the sun, so you're looking back towards the Earth, you're right in the middle of the lunar night, the Earth would be fully illuminated. The Earth's about 4 times the size of the moon, and it's much brighter, much more reflective than the moon. So the land around you, the lunar surface, would be glowing with the light from the Earth. That's called Earthshine. So a longer exposure during a total eclipse of the sun reveals the detail on the moon's surface. That's exactly what's happened there. Now, you've probably seen that effect where you can see the glowing part of the moon. I don't know how well it will stand out with these lights on here. Possibly not that way. Oh yeah, oh thank you very much. I don't know if you can see it even still, it's a bit subtle. Go back to the other one there. You just about make it out there. But the dimly glowing bit, that is due to light hitting the Earth, reflecting off the Earth, illuminating the night portion of the moon, and that light reflecting back towards us. So that's called Earthshine. And when you see that effect, especially with the young lunar crescent there, that's called the old moon in the young moon's arms. I suppose the other one would be the young moon in the... But if you extend the exposure again, you overexpose. So when you go for a few seconds exposure, you overexpose the crescent of the moon, and hey presto, you pull out that wonderful detail in the Earthshine bit. So that's actually in the lunar night there. It's incredible, you can pull out all that detail. And that carries on quite a way through the phases. That's actually, it's probably about a 6-day-old moon. You can easily make out the Earthshine bit there. I think the latest I've ever got it is around 8 to 10 days. It's still there, still visible. It's not just a pretty thing to photograph either, because the brightness of the Earthshine lit portion actually is an indicator as to how cloudy the Earth is. So it may be an indicator for climate. Okay, let's move on to the telescopic moon. So what you'd see if you look through a telescope at the moon. The moon's a gorgeous thing to look at through a telescope. And the first question that comes up for somebody who's got a telescope, who's got it out of the box, is when is the best time to look at the moon? Invariably, when you get a telescope, the moon always appears to be full in the sky. I don't know if there's any correlation. There needs to be some research done into that, but it always seems to be there pretty full in the sky. People think, wow, a full moon, that's got to be the best time to look at it. But it isn't. And the reason for that is quite simple to explain. It's because the sun's light comes straight down onto all the lunar features, and there are no shadows cast by them. So all you're seeing are reflective features, albedo features, as they're called. But if you wait until the terminator, that's not the Arnold Schwarzenegger variety, but the line running down between the lunar night and the day is visible, then anything which is close to the terminator on the day side will have the sun quite low in its sky. So these features will cast very dramatic shadows away from the sun, actually that way, along here. So if the terminator is around, that's the best time to look for features, look for them along the terminator itself. Now if we go back a completely opposite what I just said. If you want to look at the moon when it's full, the thing you see are the reflective features. So you see these dark patches here, which are the lunar seas, or the rilles. And these are basically huge impact basins where something has hit into the surface of the moon, it's depressed the surface, cracked it, and then lava has welled up, dark lava has welled up, and it fills those basins up, so it fills them nice and smooth along the top. Except that when the terminator goes close by, you start to pick out detail on the floor of those seas. You start to see wrinkle ridges where the lava has contracted as the sea has cooled down. So they start to cast shadows along there. And because the basins are due to huge impacts, the material which is thrown out as the basin is formed often forms rings around the edge of these seas, and they form beautiful mountain ranges. So again, when the terminator is close by, it's a great time to look for those. But of course, the main thing that you pick out when you have a telescope and you're looking at the moon are the craters on the moon. And there are an inordinate number of craters which are absolutely amazing to look at. I was talking to a lunar geologist the other day saying how wonderful all these different craters are, and she turned to me and said, well, actually one crater is very much like another to us. It's just the material in them we're interested in, we're not interested in what they look like, which is a great pity. Because they are gorgeous. This is Copernicus, this crater. I think it's about 90 kilometres across, if I remember correctly. But it's a classic sort of splat crater. Something's gone into the moon, it's made the moon's surface liquid as it goes in, as the impact vaporizes. That liquid surface then swings back after the impact and causes these beautiful mountains to form in the centre there. And then we've got these very impressive terraced walls around the outside. And you can start to see ejecta, which is being thrown out as well. And because all craters are different if you look at them visually, if you look very carefully at this one, it's a very strange Copernicus because it's got a quarter of the floor which is nice and smooth, and the rest of it is all rough. What's happening there? Well, it's probably something to do with the impact direction. But it is interesting because it gives them all their own individual characteristics. So if we go back to the full moon again, bad time to look for these features because you don't get any of the shadows, it is a good time to look for the rays which are around some of these craters. There's Copernicus there, and you can see the ejecta rays which are coming out. But the one which really stands out is this amazing feature here, which is Tycho. And Tycho is a very relatively young crater. All the stuff which has come out from it is still very light in colour. It will gradually go darker as it's weathered from the sun and wind over time. But at the moment it's fairly light, and they go on for miles and miles, these rays. You can see one going up there across the Serenitatis, an inordinate distance away from Tycho. Somebody wrote into the More Moon Marathon, which we've just done on the sky at night, and said if the moon was a fruit, that was the place where the stalk would be. It was hanging from the tree. That's a lovely way of describing it. Big tree. Now there are lots and lots of different craters. I haven't got time to go through all of them, but here's a couple of interesting ones which I like. There's Gassendi there, a very beautiful crater, which has got a very interesting floor. It's got the mountains in the centre again, but the floor is covered in lava, and something has caused a bulge in the lava, and it's all cracked open. So there are loads of rilles and cracks in the centre of that crater. And this one here is called Schiller. And Schiller, to me, always looks like some giant moon creatures come along and just put an enormous footprint on the lunar surface. Perhaps that's just my imagination. But it is interesting as well because Schiller doesn't have a central mountain, it has these offset mountains off to one side there. And there's that's Ptolemaeus, which is a crater, a huge crater, where lava has come in and filled the crater and flooded it. So the floor of the lava is completely smooth. But a new crater has come in on top and made an indentation. Now when the terminator is very close by to these craters, which have been smoothed over with lava which has flooded them, you can sometimes see some of the evidence of ghost craters which are underneath, which have been filled in by this lava. Can you see one there? That's pretty obvious. But when the terminator is very close by, these all begin to appear. They're great to look at, very dramatic. And then we have the oddities, like Hermite. Now Hermite is a libration zone crater. You can only get it when the rock and rolling of the moon is in the right position. But Hermite is in the northwestern part of the moon's face as we look at it, and it's odd because even though every feature on the moon is illuminated throughout the lunar cycle, some of the craters close to the poles have their walls which cast shadows inside them, so they don't always get a lot of sunlight. And in the case of Hermite, there are regions where the sun never ever is able to fall. And for that reason, those regions are very, very cold. In fact, the shadow regions inside Hermite are amongst the, or actually it is the most, or the coldest recorded place in the solar system. Minus 248 degrees centigrade. That's about 24 degrees, I think, cooler than the surface of Pluto. And they are very complex in places as well. There's the crater Janssen, a very old crater, and interestingly here we've got Fabricius and Metius which are overlapping it. So those craters must have formed afterwards. And if you can work out which ones are laying over which other ones, you can gradually work out the relative ages of all the features on the moon. And that's exactly how they're dated. Okay, so moving on now to mountain ranges. I said you get mountains around the edge of these huge seas. There's the Lunar Alps, a very famous mountain range on the moon. And you see what I mean about the Terminator being close by and casting these amazing shadows across the floor of the Mare Imbrium in this case. In fact, when the shadows are cast across the floor of the mare, the floor of the mare acts like a screen, which actually makes them appear even better. We've also got valleys. You saw a valley in that last photograph. In fact, it's this one here, with a magnified version down there. But if I look at the one on the left to begin with, that's one of my favourite valleys on the moon, the Vallis Schroeter. Well, it's not Vallis Schroeter, it's the Vallis Rita, sorry, which is actually a crater chain valley. And the reason why it's one of my favourites is it's one of the first features I ever tried to draw on the moon's surface. Yes, I have been able to draw as well. And this is an incredible feature. This is actually basically a crater chain. It was formed probably from an impact from Mare Nectaris. Something was formed with Nectaris probably, throughout a load of boulders, huge rocks, which have come along and they've formed these craters down here in this enormous chain running together. This one, on the right-hand side, is the Alpine Valley. That runs through the Alpine range that we saw earlier on, connecting Mare Frigoris to Mare Imbrium. It's a bit like somebody's carved a road across the mountains. And it's an amazing feature. This is known as a graben. And this is basically where you have two fault lines which have occurred in the moon's surface, and the material between the fault lines has just collapsed down. So it's all collapsed together, and you get this flat valley floor. And if you look very carefully, you can almost see the crack which runs down the centre of that valley. That's actually a real feature. It looks like a stream. It looks like the stream which is valley, but it's not. It's probably a collapsed lava tube. But it is a very, very narrow feature. It's about 700 metres across, and it's regarded by some to be the rite of passage of high-resolution imaging of the moon. If you can get that, you're on your way. Rilles and faults. Well, there are lots of rilles and faults. Rilles are basically cracks in the lunar surface, and there are other faults as well. Like this is one of my favourites. This is the Hadley Rill. And this does look like a river meandering around the lava. But it's not, again, this is probably a lava tube, hot lava, running underneath the surface of the main surface lava, and then it's collapsed down. It's called the Hadley Rill because it sits very close to Mons Hadley, one of the big mountains in the Apennine range of the moon. And it's also the place which was visited by Apollo 15. They landed about there. And what's interesting about that is that because they were there, they were able to take photographs of it from the surface. And there's a photograph of it from the surface. So we get to see it from Earth. You can see it through your own telescope. And you also can go online, whatever, look at the archives for Apollo 15 and see it from the surface perspective as well, which is incredible. There's a very classic fault on the moon's surface. This is Rupes Rector, or the straight wall. And I like this feature a lot. It's basically where one half of this large plane has collapsed down, and it's left what looks like a wall, but it's not. It's actually a slope. And when the sun is over in this direction here, shining onto that slope, it's illuminating the slope sort of at right angles with the slope, so the slope looks brighter than it would normally. So you get this bright effect running down here. When it's over this side, it's illuminating it and casting a shadow down the slope, so the slope looks dark. In reality, that slope is actually really gentle. It's only about 8 degrees, sort of a bit like that really, so it's a very, very gentle slope. But the shadows sort of give you a view that is much more dramatic than it really is. But what I also like about this is a strange imagination when you look at these things through a telescope for a long time. The Staghorn Mountains down here look like the handle of a cutlass. It looks like you can grab that and then you can go off fighting. Well, no, it's big, but you see what I mean. I need to get out of that. Volcanism. There's lots of volcanism on the moon, but it's quite subtle. The craters and things are impact features, but there are other features which are examples of volcanic activity. Lunar domes, for example. This is one of my favourite areas of lunar domes on the moon, the Hortensius Omega dome field. That sounds like something out of Doctor Who. Basically, these are shield volcanoes. So basically, there's a fissure where material is flowing up, and it's quite thick, viscous lava, and it just sort of sits in a mound and gets built upon. And we get shield volcanoes like that on the Earth as well. And if you look at it in detail, you can see that these domes here, they've all got summit summit pits. There's one there, one there. That one's got 2, and that one hasn't got any. What's going on now? Here's another example of volcanism on the moon, Alphonsus, which is this crater down here. If you zoom in on it there, you can see these dark patches here. These are due to pyroclastic fire fountains, where material, dark lava, has welled up from underneath and created a spray and halo around each of these fissures. So there are subtle indications of volcanism on the moon. Now, I've mentioned relief features. Those are the features with all the shadows, etc., that you've seen, which I've just shown you in those photographs. But we also get albedo features, which are purely reflective. This is my favourite. This is one's called Rainer Gamma. It has no height to it whatsoever, so if you actually look at it in the terminators nearby, it doesn't cast any shadows. It's purely because there's bright material there and dark material underneath it. And the mechanism for formation of this is believed to be something slamming into the back of the moon, throwing or putting a shockwave through that focused to this point on the lunar surface, which caused dust to be lifted up. That dust would be electrostatically charged. There's known to be a magnetic anomaly there, and as the material has come back down, it's swirled around, creating these rather beautiful patterns. There are oddities on the moon as well. This one is called, you can't guess, the Lunar X, because these craters, when they're illuminated just for a very short period of time, look like the letter X. There are other letters that people have seen as well. So they're great things to try and hunt down if you can look them up and work out when they're going to appear. As I say, I need to get out more, and sometimes my imagination runs a bit mad as well. Okay, so I'm just going to end off with a quick bit about high-resolution imaging. Now, one of the problems of getting the image scale up, so having a longer and longer focal length, is that the atmosphere gets in the way. And if you've looked at the moon through a telescope, you'll see it shimmer and distort and twist, etc., etc. And the reason for that is due to the atmosphere. Between you and the object you're looking at, you've got up to about 100 meters, you've got local seeing, which is the word given to all the wobbliness of the atmosphere. And that will be due to things like large areas of tarmac, a jacuzzi down the end of the garden, central heating in your house, for example. Higher than that, up to about 2 kilometers in height, you've got topographic seeing. And this is due to things like hills, mountains, lakes, the sea. That can affect the seeing at that height. And here in the UK, we're even luckier because we get the jet stream, which is a meandering, high-speed column of wind which gets in the way, and that causes a tremendous amount of difficulty. It's like taking an encapsulated sheet and trying to read it at the bottom of a fast-moving stream, and that's in the way. Also, the altitude of the object you're looking at will make a difference, because if you look at low altitude objects like this, the amount of atmosphere you have to look through is larger than it would be if it was overhead. So it's good to wait for things to get higher in the sky if at all possible. Also, if you take a telescope out from a hot room and you put it outside in the cold, you'll have internal seeing going on inside the tube. So you need to leave the telescope outside for a good hour, 2 hours, 3 hours, even 4 hours with really large telescopes to allow it to reach equilibrium. Now, the sort of camera you need to do high resolution imaging really needs to be something like this, not particularly that brand, I've got associated with them directly, but that's a high frame rate camera. So this is basically a movie camera which takes still images very, very quickly, one after the other. And the reason for that is that when you have all that distortion occurring, there are moments when the seeing actually looks okay. And if you take a movie of that period, you'll capture a few frames which will look undistorted. If you put that movie through a special program, there are lots of freeware programs that can do this, like Registacks, ABI Stack, and Auto Stacker. They can pull out the good frames, they can align them together, and they can average them. And that gives you a much better result than you thought you would ever get. Another trick is if you're using a mono camera without an infrared blocking filter in it, that's important, you can fit an infrared pass filter to the front of the camera, because the longer wavelengths actually are better working with the seeing. They actually stand up to the seeing better. So a red filter or an infrared pass filter will give you a better result. If you want to increase your focal length of your telescope, it's not enough for you, you can get an optical amplifier like a Barlow lens or PowerMate and stick it in the eyepiece holder and then put the camera in against that. So for example, if you have a 2,000 or a 1,000mm focal length telescope and you stick a 2 times Barlow in there, that will double the focal length, the effective focal length, giving you a 2,000mm focal length. Okay, well I'll end just talking about a big problem with actually getting in close to the moon to take high resolution images, and that's that you don't often cover enough of the surface. So what do you do about that? Well, the way around that is to join the photos together. You can merge them together in what's known as a lunar mosaic. And the technique for creating mosaics is quite simple. It's a bit like a giant jigsaw puzzle. You basically, with an editor, you put the various bits together in different layers and then align them properly, and then just take an eraser, set on say about 10%, go around the edge to get rid of any sharp edges, and then just merge them together. Gradually build up the image, and it doesn't build the entire thing, don't worry, I haven't finished that one. The sort of frame size that you're looking at will be like that, with a tremendous amount of detail in it. So the final image will be huge. And that brings me to the last problem I want to bring up, which is how to display your lunar images. Well, the first thing I'd say with any astronomical photograph you take is to put the date and the time of the photo was taken on the image, because they'll be useful to you, but it's also useful to other people if in the future there's something interesting in that image and they need to know when that was exactly taken. So always do that on your images. But one good way to display these huge mosaics that you can start to generate when you get used to imaging the moon is to go online and use a facility like Zoomit, which is a Microsoft. It's a free facility. You can submit your images to Zoomit and it will sort of do some jiggery-pokery with them, and then it will give you a link which will allow you to see your image, and you can send that link to anybody to display what's happening. But you can also interactively then click on the image, and it will allow you to zoom in to the full resolution of the image and pan around the image, so you can display it off to its absolute best. I've tried to cram an enormous amount in 30 minutes there, so I hope that was okay for you, and with that, thank you very much for listening.